last week we started we defined the means and variances of probability distributions, both discrete and continuous. Right? It turns out that the meaning is the same, right, whether it's a discrete distribution or a continuous distribution. So what is the mean? In words, the mean is a center of mass. And the variance is what? The spread. So these are the two things that you have to always remember about mean and variance, and these are very likely questions on an interview, right? So if you look at I think what we did the other day was to give some examples, but let me take this variance in a little more detail and couple of minutes spend a couple of minutes on it. The sigma x squared, right, the notation, and this is for the random variable x, of course, and then here we have mx. So the variance for some distributions, right? So supposing for some let me write it like, say first let's say the simplest ones, like the uniform distribution, for example, AB. Does anyone know the expression for the variance? Well, since nobody is answering immediately, let me say b minus a divided whole square divided by 12. So what does this tell you? What information do you get from this expression? The variance depends only on the width of the distribution, does not depend on absolute values of a and b. So you can shift the distribution up and down, the variance will not change. There is going to be a more general result that we will see. Right? The mean, of course, will always remain in the midpoints. Obviously, if you shift the distribution, the mean will change. But so for the mean, actually, the value, that is the origin of the or the distribution, that x equal to 0 value is of great significance. That determines the influences the mean, but the variance is not dependent on where you put the origin of the x-axis. That's what I want to say. Then I am looking mostly at the continuous, look at a mix of continuous and discrete. Right? The idea is that you should erase these distinctions and look at a holistic view of mean and variance. So supposing I say x is Poisson. So for the Poisson case and the exponential geometric and so on, you have they are all single parameter distributions. The uniform, it turns out, depends on two parameters a, b, right. Now for the Poisson distribution, what did we say about the mean? We said the mean was lambda, right? That's mx was lambda, we already talked about that. Variance is what? Is also lambda. So I am listing values of sigma x squared here, not not equals here. So okay, this is the values of sigma x squared in this column, right? The variance in this column, right? I have to be very careful not to confuse what gets recorded. So the variance is also lambda. So sigma x squared equals mx equals lambda. This may look a little funny, but this unfortunately or fortunately it's the way it comes. So if you increase lambda, you end up increasing both the mean and variance. You push the distribution to the right and you also end up spreading it, right? And remember, right, the Poisson distribution works for an enormously large range of values of lambda in practice. You can get absurdly small values, you can also get very large values. right. Okay. So then if I look at the exponential, for the exponential we said the mean was 1 by lambda. The variance is 1 by lambda squared. So note that you get a lambda inverse of square. So as you make the lambda smaller and smaller, you get larger and larger variance by the square, right. So so if you make so what happens is, of course, the distribution starts to spread quite rapidly as lambda becomes smaller and smaller. Okay, then the Gaussian, which I am going to stop with Gaussian. So these two are single parameter distributions, right. Where again I want to point out geometric also I can write down here, but I am not going to write. Geometric and exponential are very similar in behavior in many ways. The geometric variance is 1 minus p by p squared. So again you get that 1 by p squared, 1 by lambda squared kind of behavior. Lambda and p are kind of are very similar parameters in the two distributions, right, for geometric and exponential. P becomes small, variance of the geometric will become large, mean also becomes large. Lambda becomes small, same thing for the exponential. Okay, so let me, as a last example, and just let me say x is m sigma squared. Of course, we have sigma squared as a variance here. So here again, right, you have the two parameters, you have a perfect decoupling between the mean and variance, right. The parameter m affects only the mean, and the parameter sigma squared is only the variance. So so you can set the mean and variance independently in a Gaussian distribution without choose one without affecting the other. Okay, so let me, so with this thing I hope intuition is achieved. So we will move on to, instead of taking up more computational examples, which is not again the main point of what I am trying to do here. So anyway, given that I suppose by now you have written down all the formulas that apply, right. So I am not going to write them out here again. Instead, let us move on to some general properties, right, in the sense of this Ex squared is always greater than or equal to sigma x squared. Ex squared is always bigger than equal to mx squared. Why? Because what is Ex squared? Exactly equal to sigma x squared plus mx squared, and this is a relation between non-negative positive quantities in general, right. So the difference here is sigma x squared, and the difference here is the mean squared. So when is Ex squared equal to sigma x squared? For any zero mean random variable, Ex variance is exactly the same as its mean squared value. So I can have mx equal to 0, which means this will be equal to that, right. So remember, right, this particular thing may be is clearly the in the more it may be a little more counterintuitive of the two, but it is true, right. And it even for a simple Bernoulli distribution with parameter p, you can appreciate why E of x squared has to be bigger than mx squared. What is there? It turns out both E of x and E of x squared are both equal to p. But what is E of x the whole squared? What is mx squared? It is p squared. So what happens to a number between 0 and 1 when you square it? It becomes smaller in value, right. So you can see why that E of x squared is always bigger than, or at least no smaller than mx squared. Supposing they are equal, in other words, if E of x squared you get this with equality. What does this mean? What does this mean? When is this right? Or supposing you take a limiting case of sigma x squared becoming very, very small. All the probability is concentrated at one point. In fact, the randomness keeps reducing. There is no spread in the PDF in the limit as sigma x squared goes to 0. So you can say that x, this is the probabilistic statement, then x will be equal to mx with probability 1. That is, the probability that x is equal to mx is unity. And this is also, right, a statement in the limit. So as you consider a sequence of PDFs, that's something which we may talk about towards the end of this course, right, or PMFs, sequence of distributions indexed by some parameters such that the variance keeps decreasing as you go further and further into the sequence. Then there is no, you have the inescapable conclusion is that the random variable is taking values closer and closer to the mean and with very high probability. So this is what in fact is at the bottom of things like the law of large numbers. That's hopefully we will talk a little bit about it before we sign off in this course. Okay. Okay, then what else do I want to say right now in terms of summarizing some properties of mean and variance? Okay, let y be equal to x minus a. Supposing I just construct a simple, right, do a very simple transformation, just do x minus a. So it turns out if I do this, I do not change the variance of x. In other words, this implies that mean of course will shift, but the variance will remain unchanged. This you can please check this if you are not, right, it is very easy to plug in the formula, go here and plug it in, right, write sigma y squared in terms of sigma x squared, you will see they are exactly identical, exactly the same. So this kind of manipulation is very useful in the continuous case, right, where x takes a continuum of values. It is also applicable in the discrete case, but in the discrete case usually you have integer what you call domains, right, for the omega x that is x taking values in integers, but a can be some non-integer number as well. So if you remember, right, for example, if you take the binomial and you subtract some you subtract let us say whatever some 3.5 like that from each value of the binomial, that is what we are doing when you do x minus a. You do not get an integer valued random variable at the output of that. So y will not in general be integer valued even if x is integer valued when a is some arbitrary number, but the result is still perfectly valid. There is no problem with the result. Okay, now let us look at a more useful version of this, a slightly expanded version. Supposing I say y is ax plus b. Now remember this a and a are different, but it is better to write it as ax plus b rather than bx plus a, right. We are more interested in, I think we did the same thing earlier. So let us look at ax plus b. How does this affect this operation, how does it affect the mean and variance? Mean is very easy, all you have to do is apply E on both sides, use lotus, and what does it end up in? A? I am assuming you know mx and sigma x squared. So in terms of that, a squared. Not a squared. That is right. Right. Sigma y squared is a squared sigma x squared, does not depend on b. Again, because I have to go a little fast, I am not putting all these derivations, but it is actually quite simple. All you have to do is first get E of y squared by just simply squaring both sides of this, and if you square both sides you get a squared x square plus 2abx plus, then you take expected value on both sides and then subtract off my squared, which is square this, and you will find that the b squared will cancel and you will be left with exactly this. So, this combination of scaling and shifting only changes the variance, it does not change the mean, it changes only the mean and leaves the variance intact. So, why is this useful? It means that, for example, in the Gaussian distribution I can go very easily back and forth between arbitrary mean and variance and 0 1 mean variance. Okay. Supposing x is Gaussian with mean m, sigma squared variance. Now I have already pointed out this kind of thing which is a generalization of this. This is a shape preserving transformation. We mentioned this very clearly when I talked about transformations, right. So the shape of the PDF is the same. So in particular the Gaussian will remain Gaussian, y will remain Gaussian. So what is, but supposing I choose supposing I choose, then I let y be equal to x minus m divided by sigma, not sigma square. If I define y as x minus m by sigma, so x minus m by sigma is a special case of this, isn't it? So what happens? What are the mean and variance of y? Mean is 0, variance is 1. Remember, you have to divide by the square root of the variance here, we are not calling it by the other name, but again this implies that my is 0. Maybe I should go back here and write and obviously this result works in the opposite direction as well. So starting from 0 1 you can always inject some mean and variance by going by doing this, in other words.